lovely to be here. Unfortunately, I did not bring an actual train with me to pass around. I thought it would be a little bit too big to fit in the room. I did bring some lovely train accessory bag, so I think that proves that I'm a train nerd. So we've got that out of the way, so we can move on. So yeah, I'm going to be talking to you guys about trains today because I think trains are like a kind of interesting topic that everyone kind of interacts with. Like you guys use public transit probably. You take the subway or trains, but don't really think about like how they work, why they don't work sometimes. And during the course of my co-ops, I had the opportunity to work at the TTC, the Toronto Transit Commission. So I actually worked on the signaling systems of subway trains, which is really cool. And now I know a lot of things about trains, which I've just kind of kept doing since I left there. So I thought it'd be kind of fun to talk about them with you. So I'm going to talk about signaling systems, sort of the present/past of how they work, and then kind of the future new systems, and then go through some of the challenges with you guys about designing these new systems, implementing them, and how you can how thinking about those systems can help you design other systems too. So to start, what's a signaling system? It's pretty basic. It's just a safety system that we use to make trains not run into each other. It's just like traffic lights on a road, except these ones are a little bit different and have a little bit more power, I guess, is a good way of putting it. So let's talk about your kind of traditional signaling system that you probably every subway you probably use has used this at one point or another. This is called fixed block signaling systems. So basically how this works, there are traffic lights in the system, just like on the road, but there's also some additional work that's been done on track level to kind of make the system work. So you take your whole track of trains and you divide them into blocks. And for every block you have, it can detect if a train's on it or not. So you can see that here. You got this train on here. So this block's red. It's occupied. There's a train on it. And it actually also affects the blocks behind it. So we see here there's a hatched red one, and that's just saying that there's a train on the block ahead of it. And we have a yellow one, so that's kind of a caution, slow down. There's a train a little bit farther ahead, a couple blocks ahead. It's pretty intuitive, because just like regular traffic lights, stop if it's red, slow down if it's yellow, continue going if it's green. But these ones can actually enforce what you're doing. If you enter one of the stop blocks, it's kind of like a little lever will be brought up from the train track, and it'll activate the emergency brake on your train. So that way you can't hit another train. In order to actually satisfy that constraint, what you have to do is you have to make sure that each block a train can safely stop within that block. So the block has to be at least the maximum braking distance of a train. And this is maximum braking distance in the worst case scenario. Your train's going maximum speed. It's super slippery, the worst possible condition you could think of. So in most cases, it's a lot of overkill, right? But that's what you got to do if you have this system, because this is the resolution we have, right? We don't know where a train is in that block. We don't know how fast it's going. We don't know how fast you're going. So if you want to make sure that the system is safe, this is what you got to do. So it works well, but it's kind of inefficient in terms of actually running more trains. And this system is what was it's been around for a while. It's been prevalent for, I don't know, most of the 20th century, or all of it possibly. And it's very electromechanical, right? And all the components are basically in the track itself, and there's no wider communication, right? It's just we have this track, it can talk to blocks on the track near it, and it can make a train brake, and that's it. So, we're in the 21st century now. We've been nearly 20 years into it. We can do something a little bit better, provide a little bit more information, and make a better system. So that's where moving block signaling systems come in. These are also known as automatic train control, ATC, or communications-based train control, CBTC. So you might have heard those words bandied about in the news. I don't know, possibly. So this is basically let's add some proper communications and 21st century technology to a signaling system and make it a little bit better. So we have three main components here. We have the technology that's on the track level, we have the technology in the train itself, and we have technology that's wayside, so it's off the track level, off the train. So we'll start with the train controller. Woo. So basically on the train you have like a little computer, microcontroller, or whatever, and it's tracking the location of the train and the speed that it's going at. So you have these little like transponders here in the track level that give precise location information, like a location reference, like you are now exactly 100 meters into this track. The train reads that, and then since it also knows its speed, it'll continue calculating its location based on its speed as it passes by. And then eventually it'll get to the next transponder, and that provides like, a bound on the accuracy of the location. We know we're not gonna have too much drift because it's going past these transponders every so often. So the train knows how fast it's going. It knows roughly like how much long it'll take for it to brake because it knows characteristics about itself. And it'll send the information to this wayside zone controller, usually over radio. And that wayside controller will talk to all the trains on the track. It'll get all the information, and then it'll send back, okay, you can go at your current speed, but not any faster. Or you can go 10 kilometers faster right now. Or you need to slow down right now, or you need to stop. So in this way, we're not as dependent on a human like operator, because the train is actually doing it all itself. And in this situation, we have much better location resolution. We know exactly where trains are, subject to some communication latency and inaccuracy in the location tracking. But still like much better than what we had before. So in this way, you can actually have a lot of improvements to how this works. And I'll get into that in a little second. But first, a little bit of a tangent, I suppose. What I'm showing here is sort of one way of implementing this moving block system, but it's not the only way. The only thing that matters here is the idea that your buffer between trains, what was your fixed block before, is variable, and you can change it based on the conditions that you're currently experiencing. That's why it's called moving block. There's no actual block, but the concept of the block is the same. So, tangent. Scarborough RT. So, depending on your familiarity with Toronto, you're probably going to react differently to being told about the Scarborough RT. If you don't really know anything about Toronto, you're probably like, okay, cool, it's like a train. If you're from Toronto, but not from Scarborough, you're probably like, oh yes, the Scarborough RT. I forgot about that. If you're from Scarborough like me, you're probably lost in some horrific memories right now. I'm really sorry. It really is a fascinating, lovely little train. I have a lot of affection for it. It just had some really bad things happen to it. No one cared for it for years. Just abandoned technology. It's a little okay. But the point of talking about the Scarborough RT right now is just to show you guys what I showed you back there. This radio system of transponders is not the only way to do moving block. The Scarborough RT was actually one of the first automatic train control systems in the world, which is wild because we all hate it. And it's run without drivers. There is one operator on the train, but all they do is close the platform doors. They don't need to be there. And one thing I think is really cool about how this system works, it doesn't use radio or anything. It actually has two wires, an inductive loop, running underneath that act as the communication system. And it also acts as location reference. Every so often, these wires cross, and the train can, because there's current running through these wires, there's going to be a change in flux because the wires are moving physically. And the train can detect that, and it'll know that it hit a location reference. And I don't know. I just think that's so cool because they had this problem of okay, we need a communication system. We're going to use these wires. There's delay on the track. We also need to know the location. Let's just do that using the physical properties of these wires. Such good design. Anyway, if you want to talk to me about the Scarborough RT later, I am very happy to talk about it. I actually worked on it when I worked at the TTC, so it's my little baby. Anyways, so all lovely telling you about how moving block works, but why do you guys care? So as I kind of mentioned before, it allows for lower headway between trains, so you get more service, which we all love because we all hate being on a crowded subway. We also get a lower chance of human error, like accidents, because it's all, train controlled. And you can have humans there to kind of like stand by in case of accidents or whatever, but they're not necessary. And most train accidents are caused by human error. People get incapacitated or whatever. So this actually makes it much safer, which is great, because that's what we want. You can get real-time, very, very real-time information of accidents and anomalies. You can have an operator like radio these in, but this kind of gives you better information about what's happening. And kind of what I said here, like you have other more advanced features. You can have more advanced train tracking because you already have to know where the trains are for the system to work. It also makes it easier to install platform screen doors. This is a feature that you see a lot in like Europe and Asia, but not so much in North America, which sucks because they're great for safety and accessibility. And they're a lot easier to implement with an automatic train control system because you have the train decide precisely where to stop and align better with the screen doors, which is a lot harder to do if you're just like a person pressing brake. A little bit more error. So why do we not just have this amazing new system everywhere? Like, why is it only on the Scarborough RT, not the actual subway line? So the boring and obvious answer is money in politics is hard, which is fair. But we're slowly starting to see kind of like the political will to make these systems as, a lot of subway lines are really being over capacity or at overcapacity right now. And upgrading your signaling system is still easier than building a new subway line. But this is a technical talk, not like a politics talk. So I'll move on to other problems, but specifically like what makes it hard. So these are custom systems that have like very like safety critical design requirements, right? Like you're buying these systems ultimately from some sort of vendor who specifically works on this, but you still have to adapt it to your actual subway setup, and that is hard work. And you do have to maintain that safety factor like every time. You make sure your design still is as safe as it was when you bought it from the vendor. So it's just like a very different, higher level of design that makes it harder. You're also coordinating multiple upgrades to different systems that all kind of have to work with the old system at the same time. So like, for instance, you need to get new trains that have train controllers on them. But if you install the trains, but you haven't upgraded the tracks, not gonna have a good time. Luckily, like you can buy trains that can work with both an older fixed block system and a newer CBTC system. But there's like a lot of like that sort of coordination problem and trying to like make things compatible while you're undergoing this like year-long process of upgrading. And when it comes to track level stuff, you have a limited opportunity to actually work on your track upgrades, right? Because you actually have trains in revenue service, which is just, when people are actually taking the trains. So you only have, for instance, in the Toronto subway, you have about 4 hours at night to work. And those 4 hours are more like 2 or 3 hours, because you need to set up your work zone and then strike it at the end. It's about half an hour to an hour each side. And you need to make sure that you're leaving the track in like a state it can actually run the next day, right? So you can't do anything that's too big that would take more than 2 or 3 hours to finish, because otherwise no trains can run that day, which would be pretty bad. So if you're from Toronto and you've ever been inconvenienced by a weekend subway shutdown, this is why. They're upgrading it for a new signaling system, and that's really important work, and they can do the work of like, I don't know, a month or so of nightly shutdowns in like one weekend, and they can do work that they can't do in a weekend, like it's impossible to do in a nightly shutdown during a weekend. So those are some of the like specific technical problems that come with upgrading these systems. So I don't know, I feel like I went really quickly through this, but we'll see. So takeaways from this talk: trains are cool. I hope you guys maybe know like a little bit more about them now, and when you go take a subway, you can be like, I know how this works. I know for a fact if you take the Bloor subway, my favorite, Bloor Danforth, line 2, and you sit at the front of the train, there's still like a window, you can see the track, you can see the lights, the signals on them and stuff. Very fun time, would recommend. It makes the half-hour trip to Kennedy much less boring. Large infrastructure design is really hard, so be kind to your friendly neighborhood engineers. They're doing their best. I know it's very easy to complain about the subway all the time, but sometimes shit's just hard. And I hope that it maybe makes you guys want to think about the systems around you a little bit more. I think there are a lot of like really fun, invisible design systems around you guys that, you know, if you think a little bit about like what makes them work, what doesn't make them work, how can you improve them, like what are the trade-offs of those improvements? I think that makes you like a better designer in like your actual job, no matter how related it is. And it's kind of like fun to learn this stuff, at least I think so. So I'm giving you a little bit of information about this system, so maybe you can think about other systems around you. But yeah, here are my photo credits, and thank you guys for listening.